Hi, this is a lecture on interpretable machine learning. So in the grand scheme of our trustworthy machine learning roadmap, what we're trying to discuss today is this part of transparency. So we've covered in the previous lectures security, privacy, safety, and specifically for security, we looked at adversarial examples, training data poisoning, membership inference, and also model extraction. So now we're shifting to the other half of the trustworthy machine learning umbrella, specifically talking about transparency or interpretability. And the goal that we want to achieve, or the purpose of the trustworthy machine learning umbrella goal that we want to understand is this predictions when models produce predictions in some domains, understanding what went into the decision of these models is very important because these predictions have implications on people's lives, and the implications of these predictions could be pretty sensitive. So we want to debug the situation of non-interpretable predictions when machine learning models produce outputs. So specifically, we're going to look at the following. So the first is, of course, we want to define interpretability because the terminology around interpretable, explainable, transparent machine learning is not super clear, but we'll try our best to kind of rely on a definition that would help us out go through the rest of the lecture. Motivations for model interpretability. Why do we need interpretability in the first place? And then we'll talk about interpretability approaches. What are the different techniques we will use, or how do we approach interpretability in the first place? And then we'll talk about interpretation of model decisions. So interpretability could be looked at in different ways, but the focus of this lecture would be interpreting what the model produces as an output, because you can also interpret the model as it is being trained, or you can interpret the model as an entity. So you take the model as an input and try to interpret what the model structure is, etc. But for our purpose, we're more interested in models that are deployed and they are producing a prediction output, let's say, and that prediction output has implications of people's lives, or decisions would have implications on people's lives. Therefore, we want to understand what went into these decisions. Just like when we want to know the motivation and the input that went, or the rationale that went into a decision of a person when they make decisions about other people. For example, when a judge makes a decision, or when a judge issues a sentence against a defendant, we would be interested in what the evidence was saying and what the rationale is, and also what the law says, right? And based on that, we would either accept the decision as fair on balance, or we could challenge that decision through mechanisms like appeals and so on. Therefore, although we don't have that mechanism of appealing decisions or machine learning models as we speak, but when machine learning models are used for making decisions that humans would do otherwise and have justifications for those decisions, we want to make sure that we're not falling victims of the automation, or the whatever the limitations are behind this machine learning models. So under this topic, we're going to look at two broad categories of this interpretation of machine learning decisions, specifically example-based methods. And we'll talk more about attribution-based methods, because as of now, attribution-based methods seem to be the most promising and also the most widely used. And this come in different flavors. Some are related, some are based on gradients. For example, we rely on gradients of the models as the model predicts on inputs and computes the gradient, or the central piece in stochastic gradient descent, which is backpropagation. So the backpropagation approach could also be used for explaining or interpreting what the machine learning model is trying to do. And at the end, we're going to talk about how to evaluate attribution methods, because there are a bunch of approaches that are proposed, and we keep seeing more and more explanation or interpretation methods out there. But we should also know how to evaluate them so that we can pick, let's say, a set of interpretation methods or model interpretability mechanisms that we can apply in a specific domain for a specific task under a specific set of assumptions. Okay, so that is going to be our agenda for the lecture. So I'll start with model interpretability. What exactly do we mean by model interpretability? Okay, so when you look at the literature of model explainable machine learning or interpretable machine learning, you would find different definitions, but this definition kind of captures at a high level what we're trying to do when we say model interpretability. So at the end of the day, what we're trying to do is we want to build the capability or the ability to explain predictions or decisions. So that is the explanation aspect when we talk about interpretability. And we're talking about predictions or decisions that are made by a machine learning model in a human understandable way. This is a very important part. So every attempt that we're going to make for model interpretability is centered around making the decisions of the model interpretable, understandable by a human, because we're assuming that the implication of the decisions made by the model have some positive or negative outcomes for a human. Okay, so when we talk about interpretability, we are emphasizing on the fact that high stakes decisions, where decisions that would affect people's lives, and I'll give you examples for this, and these high stake decisions require more than predictions or accuracy of the model. And in these high stakes decisions, the model prediction might have consequences on human lives. And here are some examples. And by this list is, or this set of examples is by no means exhaustive, but they kind of highlight what we're trying to achieve when we talk about model interpretability. Okay. The one natural example is healthcare. For example, in healthcare, you would use machine learning models for predictive tasks, for instance, a diagnostic prediction. So we want to predict whether a certain scan of a tumor is cancerous or not, right? And when you do this kind of predictions, and a domain expert like a doctor or a physician is looking at the output of the model, and they suspect that something is off or something is wrong because they are the domain experts, then we want the model to kind of explain itself and tell the domain expert what is going on. And that usually requires interpreting the decisions of the model. In sectors like transportation, for example, when we apply self-driving cars, and these self-driving cars have to make real-time decisions once they are on the road, just like a human driver would do. And sometimes they get things wrong. And when they get things wrong, we want to make sure that they don't get the decisions wrong next time. So we want to fix them. We want to debug them. And we need interpretation of these models that are powering applications like self-driving cars. In finance, this is also a very sensitive domain where decisions made by people in the sector, like loan officers or mortgage underwriters and so on, would impact people's lives. For example, it would impact whether somebody is going to get a mortgage loan or not, and getting a mortgage loan is a very important milestone in people's lives because it is highly correlated with home ownership, stability of life, and many other things, right? Therefore, understanding, especially when the decision is not in favor of the customer or the applicant, we want to understand what went into the decision. And maybe this would help the customer to assess their profile or their information and come back and apply again to get the loan approved. In another domain is criminal justice. In the criminal justice system, when we use machine learning models for doing very sensitive tasks or implementing or approximating sensitive tasks, such as, for example, predicting the likelihood of someone committing a crime again, as it is done, for example, in this famous system called the Compass in the United States, and that created a lot of headlines back in 2016. So, for examples like predictive paroling or applications where you would be deciding based on the model's output whether someone is likely to commit crime or not, then you could get things wrong. And when you get things wrong, it would help out to explain this to, for example, the judge, because the judge is the domain expert and knows a lot beyond what the model can see based on some training data that may not capture all kinds of corner cases. Okay. So in a nutshell, what we're trying to say here is through this like representative examples of high-stake applications that demand explanation or interpretation, we're saying that correct predictions may not necessarily imply the model is relying on the right features. Okay, so that's the bottom line here. In other words, we're saying accuracy alone is not enough. But on the other side of the coin, we also have to point out that not all machine learning applications need interpretability. So every time we talk about machine learning and we want to talk about interpretability, we are not necessarily saying that for every model prediction, we may not need explanations. In general, interpretability is not needed, for example, in applications where human intervention is not needed. There are a whole range of applications that use machine learning where human intervention is non-existent or very minimal. For example, in advertisements. So you use social media, different apps, and so on. And when you get those automated advertisements pushed to you from the platform on your app or on your device, these are most, if not all the time, these are automated. These are almost on autopilot. Product recommendations on Amazon and other platforms, these are also automated recommendations that are basically pushed based on, let's say, your recent history of purchases, clicks, and things like that. Social network recommendations, for instance, friend requests and other recommendations of groups and things like that are actually automated and they are almost on autopilot. But we also have to keep in mind what is the rationale behind not needing any interpretability for this kind of models is the fact that if the model gets some things wrong, for example, some predictions are or some advertisements are targeted the wrong way, or product recommendations don't really match your preferences or your future interests, or the social network platform is recommending let's say, the person that you don't want to be friended with. That is fine. That's not the end of the world. That's not going to affect your life in a big way, right? So the consequences are low, and oftentimes there are no consequences. The other part of the rationale is these models, before they are put on autopilot or fully automated, or they are left out to operate on their own as like virtual agents. They are well vetted models, so a lot goes into these models by way of rigorous testing and evaluation, so that we trust the model prediction. Okay. So, and again, this is not too far from reality. For example, when I look at product recommendations on Amazon, I just look at the products and I'll just make my decision as to whether that product fits my interest, my finances, and other things. Oftentimes, these product recommendations are correct because they are based on what you have seen, and you still have the upper hand as to whether you would go ahead and purchase that product. So, in a way, you have the control. And sometimes you buy the wrong product. Let's say you buy the wrong pair of shoes. That's not the end of the world. You can return the product you bought, and life will go on. Okay, so that was what was interpretability, what is interpretability, and the high stake domains that demand interpretability, and the fact that interpretability is not for every domain or for every single model. Okay, now that we know this, why should we care about interpretability in the first place? Okay, in a way, we have this is a counterintuitive question, but I think it's worth exploring a little deeper into why, because the fact that those domains are pretty sensitive and they have the decisions of models have implications on real life is a reason enough on its own, but we might have to drill a little deeper by looking at like concrete examples. Okay, so one of the legitimate reasons why we need interpretability is to debug models. Just like we need test cases when we have to test software, and we'll be guided by the failed test cases to debug our software and fix the bugs and reshape our software package. The same way, we also want to debug machine learning models, for example, whether these models are relying on the right features or not. So here is a model that is trained to classify between cows and camels. Okay, so you have 4 instances of this model. So we give it an input of a camel. It rightfully says this is a camel. We give it an image of a cow, and again, it correctly classifies this as a cow. But the same model, when I give it this input of a cow, it now says this is a camel. And again, the same model. When I give it this image of a camel, it says this is a cow. And in the very first lecture where I was covering a highlight of everything that has to do with trustworthy machine learning or AI, I used this example to highlight the need for interpretability. So when you see this as a machine learning practitioner or even as a user, you would wonder what is going on with this model, because it is predicting the right way one time and it's just flipping its decisions at another time. But for a human, these decisions are pretty intuitive or even more trivial. So what is going on here in this model? It turns out that the model is associating sandy background with camels and grassy background with cows. So, which shows that for a machine learning practitioner, it is pretty clear that the model is relying on the wrong features. Therefore, the machine learning practitioner would have to fix this model. And this interpretability of the model would serve as a debugging assistant for the model. Okay, so that's one concrete reason or use case for interpretability of machine learning models. Another use case is interpretability could be used as a proxy for detecting bias. Bias is a very important issue that we have to deal with in machine learning models. Bias is rampant. Bias is propagated everywhere. Therefore, we want to use interpretability for as a proxy to detect bias. So let me illustrate what this means. Suppose you have a model that is trained on data of defendants, for instance, and this defendants in a criminal justice system, they want to apply for a parole. So if someone is convicted and sentenced to some number of years, and then most of the time, people can apply for a parole depending on how good they behave in while they are in jail, right? So suppose this file over here is the parole application, and we can translate this into, let's say, a feature vector and feed it to the model. And the model would say, for instance, it would just be a binary classification model, which says parole is granted or denied. So in this case, let's say it just output that parole is denied. Now, and this is the explanation, okay? When we try to look at what went into the decision of this model, we see this explanation. And as you can see, race, crimes, and gender seem to be among the features used in this process, in the decision process. And specifically, race seems to have the highest signal in the decision here. So a judge who was looking at the output of this model could say, by looking at this explanation, could say, the model is relying on illegal features because race, gender, and so on shouldn't be used, because gender is also used over here. And normally, these are what we call protected classes, at least in the sense of the United States laws, where no decision should be made based on this demographic attribute, such as race, gender, and other things, which are protected classes. So the judge, if the judge is a rational judge, right, who wouldn't blindly rely on the model, would say, okay, it looks like the model is looking at the wrong features, not only the wrong, but also illegal features. So it might get the judge in trouble. So the decision is likely biased. Therefore, the judge should intervene, maybe discard everything the model is saying and rely on other like physical evidence or evidence on paper to make their own decision. Okay, so this is one other important use case for using interpretability to detect the bias. Another use case is interpretability for providing recourse. So again, assume we have a model that is operating in the financial domain, for example, for deciding whether you're going to grant a loan, a mortgage loan to an applicant or not. So we have the mortgage loan application, which again can be translated into a feature vector and fed into the model, and the model would say mortgage loan denied. And as part of the explanation, for example, it shows you that the salary of the applicant is less than $80,000 a year, and the credit card debt of the applicant is more than $10,000. So maybe these are the factors that led to the denial of this mortgage loan application, because maybe this applicant or customer is considered to be a high risk a high risk customer who is already getting a fairly low income and also carries a fairly large amount of credit card debt. So in this case, for the mortgage applicant, if this explanation is provided, the mortgage applicant would kind of do this recourse, right? And they might say, okay, I was denied because my salary was below 80K and I have a fairly large debt. Therefore, I could go and work hard to raise my salary and also maybe reduce my credit card debt and eventually qualify for getting this mortgage loan, right? So this might be a good outcome, even though the outcome at the moment is undesired for the customer or the applicant. It could be a good recourse for the customer or the applicant to use this as a feedback mechanism and work on their finances. Another important use case for interpretability is interpretability could serve as a precursor for trust. So suppose you have a model in the medical domain which consumes some vectorized version of our patient data, and then it produces, for example, whether an output which says the person is sick or not. And as part of that, it also produces an explanation, right? And when you look at this explanation, it looks like that the model's decision is based on this set of rules, which says if gender is male, and then within that, there is a nested if, which says if ID is greater than that much, and prediction is going to be sick, and so on. So as you can see, and when you look at for the logic or the rules, the decision rules for gender equals female, it doesn't really look at this ID feature. And ID is just a number that identifies patient records, and normally you wouldn't imagine or think that this would be used as part of a training feature, right? Feature for training the model. So by looking at this, a doctor would say, for example, I won't trust these predictions on male patients because for male patients, it's relying on the wrong features. So the model is using irrelevant features for male patients. And this explanation could also serve other stakeholders like regulators, for example, the FDA or whatever, right? The regulators of the sector would, if they're here to approve this model for usage, for a widespread usage, then they might say, okay, looks like this model is relying on the most absurd set of features like ID number. So I won't approve the deployment of this model in a broader context. Therefore, sometimes multiple stakeholders can benefit from the interpretability of the model itself. Another important use case for interpretability is it could serve as a precursor or a proxy for serving legislative provision. For example, suppose we have a model that acts on some person-specific data. It could be one of the previous examples, like a legal case or a loan application in finances or a medical case and so on, right? And suppose the outcome is something that is undesirable or unexpected or outright biased, or maybe it's harmful to a person or a group of people. And we have explanations, right? So the person or whoever is impacted by this undesirable or unexpected or biased or harmful decisions might claim that they want to invoke the right to explanation. And interestingly, in data protection regulations like GDPR in the European Union and others as well, we see these provisions where people have the right to seek explanations when machine learning models or generally algorithms are used for making decisions that would affect their lives. Therefore, if we pick the loan provider in this case, the loan provider could say, according to a report from some credit bureau X in the context of the United States, for instance, it might say you declared bankruptcy last year, which made your likelihood to default score higher and deemed you as a high-risk borrower, right? So the loan provider could use this as an explanation to serve this right to explanation by the customer, which is legally backed because the regulations provide this. The regulations allow or enable people to seek explanations. Okay. So that is another important criteria, another important use case that highlights the importance of interpretability. Okay, so if I have to summarize what we have discussed so far as to why we need interpretability, as you can see, there are multiple facets or multiple phases of the interpretability of machine learning models. So as we said, debugging a model is one important use case where easy debugging could be improvement of performance and robustness of the model. Detection of bias is another use case where using some features may correlate with discrimination. Trust and accountability is another one where the explanation can guide whether or not to trust a decision of the model. Compliance auditing is important for enhancing transparency and fairness. Algorithmic recourse is another concrete use case where the feedback could be helpful for users. And the right to explanation, for example, in GDPR in the European Union, and in the sense of the United States, the Equal Credit Opportunity Act is also stipulates the right to explanation. And in other countries like France, for example, we have what we call the Digital Republic Act, which also states something along the lines of the right to explanation. Okay, so that is why model interpretability is important. Okay, so now that we have enough reasons why interpretability is important and useful, now let's talk about, okay, how do we approach model interpretability? Okay, broadly speaking, we can approach model interpretability in two ways. The first approach is called inherent interpretability or anti-hook interpretability. where the idea here is we want to make the models provide their own explanations on whatever decisions they make. And this kind of models are naturally or inherently interpretable, for example, decision trees or linear or logistic regression models. And the downsides of such models is that the model's capability to do well on a task might not always work out well. For example, decision trees might struggle to deal with like complex image models. And the model could become very hard to interpret. For instance, if you take again decision trees, depending on how many layers you have in the tree, the interpretability could get a little harder. So for instance, if you have a 150 layer tree, it's really hard to kind of traverse the tree and try to interpret what is going on. The other kind of interpretability approach is what we call post hoc, which is the opposite of anti hoc. So the post hoc interpretability is the idea is to create a post hoc or second model to explain the black box model. So you would assume the model is a black box, but by interacting with the model, you can create another explainer or proxy to explain what the black box model is doing. And this is usually done through surrogate models, just like the mechanism is similar to what we do in model extraction attacks when we build substitute models by talking to the black box or a target model. And you could do many techniques like feature importance analysis, but we'll talk about specific approaches to do this. You can do layer-wise importance propagation by going through different layers. And one disadvantage or con limitation that we have for post-hoc interpretability is you are expected to interpret millions of parameters. For example, for deep neural networks, this might become a very daunting task as to how to explain millions of parameters. And today we have models like large language models with billions of parameters. So interpretability becomes a very hard problem. Okay, regardless, we do have these two broad approaches of doing model interpretability. So let me expand a little bit on each of them. So the inherent interpretability approach is, as I said, using models or model architectures that are easy to kind of understand as to the decision boundary, for example, linear models or linear regression models like the one you see over here, or decision trees, because when you interpret decision trees, when you predict an input on a decision tree, you oftentimes start with the root of the decision tree, which is the most separating feature as a root of the tree, and then you keep traversing the tree based on values of features, and you end up with a leaf node, which is going to be the prediction of the input. And that path you traverse is basically the explanation of the prediction. You could also use what we call decision rules. And these decision rules are just a bunch of Boolean expressions that would be evaluated to true or false. And this is also very intuitive and pretty close to what humans understand, because remember, the central goal of interpretability is to produce explanations that are understandable by humans. Therefore, it serves that purpose pretty well. Okay, so that's sort of examples of how inherent interpretability could be achieved. The post-hoc interpretability, as we said, is we have some black box model, and we have to produce some explainer, which could also be a model in itself, like a surrogate model, a subset model. And we produce explanations like this one or like this one. And the person who is looking at this would say, okay, now I understand why we are getting this kind of output. The post-hoc interpretability approach has a range of possibilities. So we call it the post-hoc interpretability spectrum. So the idea is if you have the model on this side, right, and the input on this side, so when we are looking at inputs, for example, images, we're looking at what representations have the model learned at a low level, and we have this part, and in the middle or at the intermediate level, what pattern or image maximally activates a particular neuron, right? And then at the input level, what we're trying to do is we are trying to understand or explain why input X has been classified as, let's say, number 3 in this case. So the red regions or the heat map here is showing that, the pixels highlighted in red and some of which are highlighted in orange correlate with the prediction that we're looking at. Okay. So that's the spectrum. You can start with the input and you can go to the model, right? The post-hoc interpretability spectrum, when you look at it differently, you can classify it into 3 stages. So if you start with a model, you're basically understanding what is the boundary between 2 or whatever the classes are. So in this case, the green dots and the blue dots, so the green dots over here, we have this boundary that is separating the 2. And in the middle, what you see is for each class, you are basically looking at what is the faithful region that is kind of characterizing a specific class. And when you look at the input, you're basically looking at the prediction of the input and trying to see which other inputs are close to that input when you explain, right? So explanation could be looked at different layers of granularity, either at a high level where you look at the decision boundary, or at a specific class, what is faithful to that particular class, for example, the blue dots, or the input and then the neighborhood of the inputs in that class. When we look at inherent and post-hoc interpretability, and in some settings, the accuracy interpretability trade-off is important. For instance, some models, when you look at accuracy and interpretability, and you try to kind of analyze the trade-off between these 2 requirements, because you want the models to be accurate on the task and also at the same time interpretable, but not all models may satisfy this property. So some models are highly interpretable, but they come with low accuracy, right? For example, linear regression, decision trees, and so on. Some are somewhere in the middle, for instance, support vector machines. But some others come with high accuracy, so they predict inputs with high accuracy, but they are low on the interpretability end, right? So so you might have to make a trade-off between these 2 properties or goals you want to achieve. When your goal is to build an inherently interpretable model, you can rely on the simple models like the one you see on the left here. So you can build interpretable and accurate models. But on the right, what you see is a very complex landscape of decision boundary, where the complex model might achieve higher accuracy, but it may not be super interpretable. So in summary, when we analyze the inherent versus post-hoc interpretability, if you can build an interpretable and accurate model, that is the ideal case. You go for it, because this fosters trust and ensures transparency in the eyes of the user. But otherwise, you have no choice, you're going to resort to post-hoc explanations. And this is a pragmatic compromise that you have to make for complex models. For example, right here, if you're using deep neural networks for image classification models, and you know that they're good in terms of accuracy, then you have to live with low interpretability, or you might have to work on simplifying the model architecture so that you don't have millions of parameters, okay? But the bottom line here is that you have to be pragmatic, and you have to be willing to compromise, because there is no free lunch in the space of trustworthy machine learning. Okay, so that is as to inherent versus post-hoc interpretability approaches in interpreting machine learning models. The other useful question to ask at this point is how to evaluate interpretability. So this is still emerging, but as of now, there are 2 approaches. So either you evaluate in the context of the application, and another way to say this is you will know when you see it. So you will know the model got something wrong when you see it. For example, if you're a domain expert, like a judge or a doctor, you would see something off that goes against what you've learned in your discipline, in your domain or in your training, right? And you would say, oh, this doesn't make sense. The other approach is you evaluate through some quantifiable proxy or metrics. And another way to say this is you will know it when you measure it. And I'll be saying more about this. But in general, we have two approaches of evaluating in the context of the application or evaluating through some quantifiable proxy that seems to capture what the interpretability or the quality of the interpretability is. Okay, so with that, we're going to move on to how to do the how to interpret model decisions, because as I said at the beginning, the focus of this lecture is on interpreting decisions of machine learning models. Okay, so the first class of approaches that we're going to talk about is what we call example-based. So the idea with example-based approaches is the question that we're going to answer is which training instance influenced the decision the most, okay? So every time we get a decision or a prediction out of a model, the question we ask is, are there other inputs around this input that influenced the decision of this input? And the way this is done is by computing what we call influence score for the input. So the influence score for the input. And also note that this doesn't specifically highlight which features are important. It simply tells you examples of inputs that influenced the decision. So for the prediction that says sunflower with this much confidence, so that's our prediction over here. These are the influence scores that are provided for different inputs. As you can see, this influence score is 0.09, fairly low, right? There's another influence score, which is 0.14 of another input. And there is influence score of 0.42. Among the three, the highest one is this one. And this seems to be close to the sunflower that we see in this image, right? There is some sunflower over here. There seems to be some yellow stuff over here, but it's not clear whether this is a sunflower or not, or it might be some version or some flavor of a sunflower. But it apparently is the case that this third image on the right is the one with the most influence score. And influence score could be computed in different ways, but you can rely on the gradient of the loss function for the input. And you can compute this with respect to what we call the Bayesian metrics. So the Bayesian metrics over here is the inverse of the Bayesian metrics multiplied with the gradient of the input. The loss based on the input would be a way to compute. One way you would compute this influence scores. And remember here, it doesn't specifically highlight which features are important, but this is one way to look at interpretability. The other widely used approach is what we call attribution. So attribution is going to work as follows. So the key idea behind attribution is you're given an input, let's say an image that comes from some domain, and a decision function, let's say a classifier, right? And the goal is to assign each pixel in this, in general, each feature. We're saying pixel because we're talking about images here. So we have, let's say, n features or n pixels, so x1 to xn. We're going to assign what we call attribution values, r1 of x, r2 of x, up to rn of x, such that every pixel is going to be annotated with an attribution value. And the attribution value is actually a score that we're going to give to indicate the importance of that feature or that pixel, in the case of images, to the decision that we're looking at. For example, here is a number 3 over here, right? So this is number 3, and the white portion shows the part that highlights the number 3, and the background is black. So we use every single pixel, black and white, and we're going to give it a score. So as you can see, the white pixels should be scored higher because the white pixels correspond to the region covered by the number 3. So as you can see, the white pixels are of higher attribution values, right? And the black pixels have lower attribution values, oftentimes close to 0. And you can also do a histogram of the features, the pixels. Sorry, this is actually the prediction output f of x. That shows a histogram score of probability distributions and showing number 3 being the maximum. Okay, so that is the key idea behind attribution. Okay, we're going to spend more time on attributions because they are the widely used approach for model interpretability. You can also visualize attributions through heat maps. Suppose you have this number 3 over here, right? And you can do the attribution using a heat map where the parts that are covered by the number 3, the blue, green, and yellow parts over here, depending on the score. For example, the yellow is the highest scores, and green seems to be the second highest, and so on. Those would be used to highlight the parts of the image through a heat map. And as you can see, the purple region here has very low scores, which corresponds to the black pixels on the original image of number 3. So you can also do attribution using heat maps, and heat maps are oftentimes pretty intuitive to look at because the region that is relevant is highlighted with high scores or a different color. When you look at these attributions visualized as heat maps, here is an example of different approaches of doing attribution and showing the heat map. So on the left is the original image. So the label is a garter snake. So this is the snake over here. So the goal is to kind of highlight the snake. And these are different approaches. So the gradient multiplied with the input is, so if you simply multiply the gradient with the input, that could serve as sort of a baseline explanation or attribution. And as you can see, there is some portion of the snake that is highlighted over here. And we also have integrated gradients, another approach where you're trying to explain or highlight this using the heat map. And we have deep lift, which is basically scaling the input, the pixels to show the attribution aspects of the pixels as well. Sorry, my presentation went off, so I'll just highlight the regions again. Just have to get my pen. Okay. So yeah, so as I was saying, this is the snake. That was a part with gradient multiplied with input. This is the part with integrated gradients, and this is the part highlighted with deep lift, which is basically rescaling the pixels. And we have this epsilon parameterized layer-wise relevance propagation, or LRP, which is basically you propagate the gradients that you compute at each layer of the neural network. Okay, so this is another example of using different approaches of attribution for visualizing attributions through heat maps. Okay, so when I gave you these examples, I didn't say much about the specific techniques. Okay, now I'm going to talk about specific ways of doing attributions. And one of the widely used baseline attribution techniques is what we call saliency maps. Okay, saliency maps, the idea of saliency maps is you're going to basically do the gradient of the model with respect to each input. So it's gradient with respect to the input x. And this could be computed using backpropagation, as you may know. So the saliency of an input x would be the gradient of the gradient of the gradient of the model with respect to the function x. And as you know, this is a partial derivative of the model with respect to the input x. But as we know, or we may not know, saliency maps are noisy. Okay, so saliency maps, what you see on the right is saliency maps. So this regions over here, this regions over here are actually silency maps of the different images. For example, here we have a washer or a dryer. It looks like a washer. Here is a silency map. And under each image is a silency map. And as you can see, the silency maps are a little noisy. So they roughly correlate with the object of interest in our case. And the question then is how to improve silency maps, which is basically which means why are silency maps noisy? Okay, so if we answer the question why are silency maps noisy, we can also improve that, right? So why are they not noisy? Why are silency maps noisy? There are a bunch of hypotheses. We're going to look at three hypotheses that seem to serve the purpose here. Hypothesis one is silency maps are truthful. So, you know, they just show what is in there. For example, for this image over here, the silency map is what you see over here. So you see the white pixels highlighted based on where the animal is, okay? So the certain pixels are scattered randomly across the image, which are central to how the deep neural network is making a decision, okay? So this is a natural feature of, silency maps. So in other words, they're important because they are used to differentiate the important part of the image or the input versus the less important part. The other hypothesis is silency maps, for silency maps to be noisy is the fact that gradients are discontinuous. Gradients are not smooth because deep neural networks use this activation functions, which are piecewise linear. For example, if you take the ReLU or max pooling functions and you zoom in on in the middle of these functions, you would see a linear or a straight line, right? So sudden jumps in the importance score over the small changes in the input happen, right? So here's an example of, a shallow model over here and a deep model on this side. And you can see how the gradients become very discontinuous as we go to deeper models. Okay, so this is another theory or sort of a hypothesis that gradients are discontinuous. The third hypothesis is the function just saturates. In other words, what we're saying here is a feature may have a strong effect globally. Okay, so over here, for example, a feature has a strong effect, but with a small derivative locally. So when you look at the features derivative locally, it's so small, okay? So that is another theory or hypothesis around the fact that saliency maps are noisy. Then the question is, okay, now we have a bunch of hypotheses. How do we improve saliency maps? So there are two ways you can look at the improvement of saliency maps: gradient-based approaches and backpropagation-based approaches. So given the saliency map formulation that we discussed earlier, one way to improve is to add noise to saliency maps. So you're going to perturb the input X to X star and use, instead of computing the gradient of the input X, you're going to compute the gradient of the perturbed version of the input. And you can do this you can do the perturbation of the input or the adding the noise multiple times for the same input, and you can do the average. Some methods do the average as well. The other approach is you want to modify the backpropagation algorithm such that it helps the purpose of reducing or removing noise from saliency maps. So in summary, what we're trying to say about this attribution methods is the key idea is to assign attribution score to each input pixel. The baseline attribution of saliency maps is very noisy, and we've looked at three hypotheses where the first one says saliency maps are truthful, second one says their gradients are discontinuous, and the third one says the function saturates, where a feature is globally very visible, but locally not that differentiable. So the two solution approaches that we highlighted are gradient-based methods and backpropagation-based methods. But there are other approaches that would do the same thing or serve the same purpose of attributions. For example, multiplying gradient with input is another approach. Integrated gradients, layer-wise relevance propagation, or LRP, deep tailor decomposition, deep lift, pattern net, and pattern attribution. So I highlight some of the most widely used ones here. Since we cannot cover every single one of them in one lecture, I just put a set of pointers, and we will focus on some that are worth highlighting here. So we'll start with gradient-based. So for gradient-based, the second hypothesis says gradients are discontinuous. Therefore, the solution is, why don't you smoothen the gradients, right? If they are discontinuous, just make them smooth. That's basically regularization in a different form. Okay, so the way you're going to do this is basically by adding noise, right? So by adding noise, you can smooth the gradient. So the smooth gradient function is going to be this, where you are adding noise to the original input, and you can sample this noise from distributions like the Gaussian distribution. Okay, so that's one approach. In hypothesis 2, when you do this, to tackle hypothesis 2, or to kind of fix the issue with noisy gradients, when you do the smoothing of the gradients, you would get something along these lines, depending on how much noise you're adding. So you have the original image here, and now you have noise level, right? So if there was no noise, you would get what you see over here. And then you incrementally introduce noise. So with 5% noise, you would get this, 10%, and so on. And when you get to 50%, so the more noise you add, the more fine-grained the attribution becomes, and you would also see the horn of the animal and other features like the eyes and etc. Right? So as you go to the right, which means adding more noise, you get more visibility into the important aspects or the attributions of the image. The other approach that is gradient-based is what we call interior gradient. And this one serves for handling the case where the function saturates. And what you would be doing is simply scaling. So you're going to use some scaling parameter alpha, where you would basically lift up the signal that the feature would give locally, so that the feature would be equally useful globally and locally. Okay. So the way this is done is you can basically do a partial derivative of the scaled version of the input. So x star is x scaled with some scaling factor alpha, and this alpha is between 0 and 1. So scaling with 0 means the same image or the same input, and scaling with 1 means scaling with 1 means changing the image, changing the size by a large margin. Okay, so as you can see, we have a camera up here, and you can see how the choice of alpha is going to affect the fidelity of the attribution that you would observe here. The higher, the smaller the scaling factor, 0.02, for instance, the camera is very visible. And as you increase, it gets a little distorted. And as it gets close to 1, what you see is pretty small. Not pretty small, pretty invisible rather. Okay. Okay, so that's on gradient-based. Now we have backpropagation-based approach, which is the other alternative. So in backpropagation, this draws insights from the way backpropagation happens, and specifically the activation functions that we use, right? So the ReLU and the forward pass and the backward pass that we do for backward propagation, where, for example, in the forward pass, we replace negative gradients with zero gradients, and in the backward pass, we do the opposite, right? So we keep the negative gradients and replace some of the gradients with 0. So the backward propagation approach is called the deconvolute, so the opposite of convolutional networks, so doing the opposite of convolutes. So what it does is it maps feature patterns into pattern to input space. So basically, image reconstruction is what is happening. To obtain a valid feature reconstruction, you're going to pass reconstruct the signal through your favorite activation function, for example, ReLU, as it is done over here. And you're going to remove noise by removing negative gradients. So by removing negative gradients, as you see over here, you're going to remove noise. In a way, this is just cleansing the input from noise, and that would basically clarify or make the attributions more clear. And you can do this through what we call the guided backpropagation, which means you combine deconvolute with backpropagation. So you apply the technique that we just described, deconvolute with backpropagation, and you end up with a better version of the explanation. So this is also an approach that is explored for the purpose of making saliency maps less noisy, and as a result, the attributions more clear. So when you look at this effectiveness of the different approaches, for example, this is the original input, the original image, and backpropagation would give you that, the vanilla backpropagation. The deconvolution would give you that. Backpropagation guided with deconvolute would give you this. So as you can see, the image of the head of the cat is pretty visible in this case, so the attribution is pretty high fidelity or high resolution. So basically, removing more gradient leads to sharper visualizations. And lastly, how do we evaluate attribution methods? So attribution methods, as I said, could be evaluated in a bunch of ways. So you can evaluate them qualitatively, so through metrics like coherence and class sensitivity and so on. You can also evaluate them quantitatively using metrics like selectivity and other approaches like remove and retrain or keep and retrain. So to give you a highlight of how this is done, for example, on the qualitative side, so coherence. So what we're trying to do here is attributions should fall on discriminative features. For example, the object of interest, right? So you can use saliency map over here for an image, smooth gradient, variable gradient, gradient multiplied with input, integrated gradient, the layer-wise relevance propagation, parameterized with some epsilon, and the deep lift approach. So you could see different variations of this, and this is qualitative, right? So just look at this and make your judgments as to how useful the explanation method is, whether it is coherent with what you expect as far as the region that you wanted to attribute the model decision to. Another example is class sensitivity. So in this case, we want attributions to be sensitive to the class labels. As you can see for this image of a dog, the vanilla gradient would give you that, would give you this. Integrated gradient would give you that. And guided backpropagation, as you can see, is pretty useless. And the smooth gradient, when you do smoothing of the gradient, you get a much better fidelity of the attributions. The quantitative ones could be implemented in different ways, but the idea is you're going to sort pixel attribution values, for instance, and you're going to iterate over this and remove pixels and evaluate the model and see, how the model accuracy decreases to understand the importance of this attribution values. And you can evaluate this in different ways. For example, here in the middle, you see the examples and the heat maps and how pixel flipping or removing features would affect the heat maps of the features. So basically, the intuition is removing feature with high attribution should cause large decrease in class probability. And on the quantitative front, there is a remove one and retrain or keep and retrain approaches. So sensitivity may not be accurate, the qualitative measure, and class probability may decrease because the model has never seen an image, right? And the remove and retrain and keep and retrain approaches measure how the performance of the classifier changes as features are removed. And for example, for remove and retrain, you basically replace some percentage of pixels and estimate to be the most important. And for keep and remove, keep and retrain, you're gonna replace a percentage of pixels estimated to be least important. and you retrain the model and measure change in test accuracy and see how the accuracy changes for the model. This is an illustration of the quantitative approach, remove one and retrain, where you start with the estimation of the input feature importance over here, and then you modify of input according to the estimate, and then you evaluate the model and see the prediction to see if the model is giving the right prediction or not. If it is giving the right prediction, the feature is not important, otherwise it is. And this is a plot coming from this paper that compares the different approaches for remove one and retrain, and comparison between remove one and retrain and keep and retrain. And in summary, what we've looked at in this lecture is we defined interpretability, which is basically presenting or explaining the model decision in a human understandable manner. The motivations are debugging, proxy for bias detection, or building trust and accountability, or compliance in auditing, algorithmic recourse, or right to explanation. So all these are good or important motivations for having interpretability. We talked about interpretability approaches, broadly two classes, inherent and post-hoc interpretability. We talked about interpretation of decisions, example-based, attribution-based methods like gradient-based backpropagation. And lastly, we talked about evaluation metrics that we use for evaluating attribution methods, like both in qualitative and quantitative ways. Okay, so with that, this is the end for the lecture on interpretable machine learning models. Hopefully that gave you a very comprehensive overview and also some flavor of the techniques that we use for model interpretability. I'll see you for the next lecture. Thanks.